Welcome, ladies and gentlemen, and of course, colleagues. It's my absolute pleasure to welcome you to the third of our Professorial lecture webinar series, and today's is called Life-Changing Materials. Before we start, just a little bit of housekeeping. Just so you know, the webinar will be recorded for publicity purposes. Attendees will be asked to ask questions using the Q&A function. However, Professor Rudd does have some specific questions that he'll throw out during his presentation, and we'd like you to use the chat function just so that we can capture those specific questions. But anything else, if you could use the Q&A, that will be monitored throughout the presentation, and we'll ask those questions at the end. At the end, there will also be a satisfaction poll and a survey. We'd really appreciate it if you could use that. And if there's any technical issues, we have a team on standby. If you could use the chat button for that, that would be great. Now, a little bit before we start, for those of you that don't know, Professor Rudd, let me tell you a little bit about him. So, Professor Chris Rudd OBE is the Deputy Vice Chancellor and Head of Campus for Singapore for James Cook University. Chris is responsible for the James Cook University Singapore Board for the strategic leadership of the university campus and is a member of the JCU Executive Board. Prior to joining James Cook University, Chris was Provost and CEO of the University of Nottingham, Ningbo, China from 2015 to 19, where he led a campus of 8,000 students and 900 staff, delivering UK degree programs in China's first Sino-foreign university and building a series of new research institutes in China to connect with local and international industry. His previous roles include Pro-Vice Chancellor for External Engagement, 2007 to 15, leading on business engagement and philanthropic fundraising as the Dean of Nottingham's Engineering Faculty from 2003 to 7. Chris was on the board of directors of the China-Britain Business Council from 2011 to 2017. In addition to his academic career, Chris has served as a seagoing engineer for P&O Steam Navigation Company and as a research engineer for GKN Technology Limited. He has collaborated widely with industry in Europe, the United States of America and Asia, and has held guest professorships in Canada, USA, and China. He is currently a guest professor at Jilin University and the National Level International Scientific and Technology Cooperation Base in Advanced Composite Materials, hosted by AVIC in Beijing. He received the Ningbo government's highest honor for foreigners, the Camellia Award in 2017, and the Zhejiang Province Westlake Award in 2018. He was awarded the 48 Group Club Icebreaker Laureate Prize for his services to Sino-US-UK relations and led the Nottingham Confucius Institute to model status, awarded by the Vice Premier Liu Yangdong in 2015. He was admitted to the Order of the British Empire in the United Kingdom in 2018 in the New Year Honours List for services to higher education and UK-China relations. Chris is an active researcher, holds grants and contracts with several international organisations for his research and engineering materials and lightweight structures. His team have contributed to the introduction of new materials and processes in the automotive, aerospace and medical devices industries. He has successfully supervised more than 60 PhD projects and has published over 175 journal articles with around 6,500 citations and a H-index of 43. Outside of his professional activities, Chris enjoys outdoor activities, traditional music and dance, and continues to study Mandarin at intermediate level. So without further ado, I will hand over to Professor Chris Rudd.
So thank you so much for that introduction, Karen. And I'd also like to put a big shout out to Denise, who encouraged me to pick up the baton, as it were, and also to Vinay and Erica, who have been very patient with me in walking me through some of the advanced tech we'll be using today. So I come from the UK system, and when you get appointed or promoted to a professorial position, then in the UK you will get a letter from the registrar inviting you to give an inaugural lecture. And at that point, most people then run for cover, and some people have been known to go to ground for between 3 and 5 years, at which point you would get another letter from the registrar saying, well, you know, if you don't want to do it, then that's okay. You know, we'll find somebody else. And I think I probably dodged the bullets for about 3 years before I gave my first professorial lecture, which was in, oh my God, I think 1998, I'd called Beyond the Plastic Pig. And I'm not going to take that one any further. Today, I am taking a slightly broader brush and taking a look at the world of advanced materials and trying to sort of honour the tradition of the inaugural lecture, which is to make it relevant, interesting, current, but also accessible to non-specialists. And Neil has put his hand up. I don't know whether somebody can see what we can do for Neil. So assuming the text going all right, then yeah, I'd also like to put a shout out to our advisory board members. I noticed that Phil Forrest was in the room, very welcome, and also friends from other PEIs. So great to see you all. I'm going to share a little bit of personal stuff before we get into the detail. And we all, well, many of us enjoyed Denise's sharing the other day when she talked about the importance of place. And kind of this is my place. This is the River North Tyne back in 1965, apparently laying down the law to my older and younger sister on a family picnic. And it was kind of those outings that were a beginning of a long and happy association with the outdoors. And if I scoot forwards half a dozen years, this is a place that Neil may know, which is it's the top of the Bowder Stone in England's Lake District. And spending time in the outdoors led me to visit some amazing places and have some amazing experiences. And I'm kind of using this as a hook into the start of the technical talk. And I got in my early 20s, I suppose, during my university career, very interested in rock climbing, and probably spent about the next 20 years using every free moment almost, either doing this kind of stuff or traveling somewhere to do it. And in the course of that, met some amazing people, did some amazing things, and also gained a love of traditional music and dance. And I've done a bit of sharing about that with JCU staff in the past. And so was having a thoroughly enjoyable time until these two characters came along. And of course, all good things must come to an end. And so that did slow me down for a little while. And we still continue to enjoy the great outdoors, but in a lower risk environment, I have to say. But for those of you who have got young kids, I would encourage you to cherish those years, because they do go past very, very quickly. And so long as you stay in touch with your inner core, then you will come back to it. And I'm very happy to say that when I moved to China in 2015, I very much came back to rock climbing, perhaps not quite at the same high standard, but still continuing to do, by my standards, some reasonably adventurous things. This was the first ascent of one of the many, many new climbs that we were privileged to put up in and around Ningbo. And I showed this for a pretty specific reason. So this was the first ascent of a new route. It was about 150 meters long. It took us I don't know, maybe 3 or 4 hours to climb it. But it wasn't the first time that we had been on that particular cliff, because when you establish a new route, you first of all got to clean it. And I just wanted to show you for fun some of the activities involved in cleaning a new route. And when I say clean, I'm not talking about using a feather duster. And this is just a very short video clip from one of my Chinese friend and I, Zhang Fan's cleaning sessions 2 days before the climb. So here's Zhang Fan removing a little bit of loose rock from that very same cliff. Yeah, so all good, clean fun, or not. And the reason for showing that is that in situations like that, let me find my PPT again. In situations like that, you are absolutely completely dependent on advanced materials. And it's only advanced materials that enable us to go into situations like that and operate successfully and even survive. And so that kind of is a little bit of an angle on why materials are important to me. But they're important to all of us because, you know, if you think about food, fuel, and materials in the hierarchy of needs, those are the 3 things that enable us to survive as a society. And of course, most of the materials that we employ are involving finite resources. And so what I want to develop in this talk is about why we need as a society to preserve those resources and to continually look for sustainable materials solutions that will improve our quality of life and drive economic growth and so on. And it's not just safety features like ropes and carabiners and harnesses and helmets and all of that that save lives. It's also materials that get implanted inside the body. And if it wasn't for progress in material science, we wouldn't be implanting, as it says here, 70,000 artificial heart valves every year and saving lives and prolonging lives and using complex synthetic materials to replace natural body functions. And we'll talk more about that later on. But there's also the misuse of materials. And we think about the 1986 Challenger catastrophe, where good engineering materials were used in the wrong context and resulted in significant loss of life, leading in that case to all of the astronauts losing their lives because political decisions were made over and above engineering decisions, despite multiple and repeated warnings from the engineering teams not to go ahead with the Challenger launch in adversely cold conditions. So we've got a responsibility as scientists and engineers, not just to dish up the new materials, but to make sure that they are used in a responsible manner. And one of the recurring themes I'm going to use in this talk is materials and energy use are really, really strongly intertwined for multiple reasons. First of all, the minerals industry, which of course Australia relies on so heavily, consumes about 15% of global electricity. And I remember reading somewhere that 2% of the power that is consumed globally goes in smashing up mineral ores, which is really quite stark statistic. But on the other hand, you know, materials scientists can bring solutions. So if 20% of global electricity also goes in in lighting our homes and our streets and our offices, then we've got a materials solution in the form of LEDs, which could reduce that by up to 75% if we all convert. So yes, as engineers, we're consuming energy, but we're also delivering solutions to energy problems. So the questions for us to think about in this little talk then, what do we need from new materials technology to enable our current lifestyles to continue the way that we would like? What are the new developments that we ought to be getting excited about that would enable new businesses or protect our environment or improve our quality of lives? What new material would change your life? And how long does a new material take to get to market? And we'll look at some answers to all of those questions, and hopefully maybe in the Q&A discuss some of these questions. So this fine-looking gentleman has had his life transformed by a new material. So let's have some suggestions in the chat function about what that new material might be. How has his quality of life been transformed by new engineering materials? And I'm waiting for the first suggestion there. So it could be in the form of the pan scrubber, it could be in the form of the detergent that he's using, but actually what I'm getting at here is the coating on his frying pan. So the coating on his frying pan is a material that you would call Teflon, and I as a materials geek would call PTFE, polyteflon fluoroethylene. And that is a material which has been around for not quite 100 years, but for probably the last 40 years has been ubiquitous in our kitchenware. It's been on our frying pans, on our saucepans, on our baking tins, and it's a low surface energy material that stops things from sticking to it. And of course we use it in the plastics molding industry as well to stop things sticking to our plastics mold. So it's a new material. It was discovered by accident by, I think, a DuPont scientist back in the 1930s and has been in commercial use for about 50 years. So now let's do a little bit of engineering. And this is the only bit of engineering in the whole talk, but I've put it in because it helps to explain why I got turned on to new materials, and in particular the new materials that I work on. So the item on the left is a computer simulation of a car suspension. For any of the car geeks there, it is an ancient Ford Granada lower wishbone. And I mention that because it's a component that we worked on during an internship at National Engineering Laboratory in Glasgow. And what turned me on was the fact that when you did your stress analysis and plotted those little arrows on the right, which are the directions that the internal forces are traveling through in the material, it was a revelation to me that as well as designing the structure, that you could also design the material to take into account of those stress vectors by putting in fibers, and by putting in fibers that followed the same arrows as the stress vector. And that to me was just absolute amazing revelation. And it led me to completely change my technical interests from thermodynamics, which I'd been working on before, to these kinds of materials, fiber reinforced materials, where you played around with the direction of the fibers to change the properties of the material. And it felt to me like, as an engineering designer, you were playing God with your material. And I didn't know that just before this session, Abhishek was going to be sharing on Formula One structures. And Abhishek So I now know has got lots of bits of carbon fiber reinforced plastics in his shed, if he's got a shed, or in his desk drawer or somewhere. And that's exactly what these materials are. And we will come back to them a bit later on. And so I had the privilege to be involved with development of these materials when they were going through a terrifically exciting expansion. I started working on composites in 1985, and if you look at the growth of carbon fiber composites in, at least in the aerospace industry, going from about 5% of an Airbus aircraft to more than 53%, you can see how much the market has grown and how much carbon fiber composites have gone from being a kind of exotic discovery material to being a mainstream engineering material. And so when we take a flight in A350 or Boeing Dreamliner, you know, we wish, then we are relying absolutely on structural composite materials. And Karen asked me about a particular example of advanced composite materials. This is one of the incarnations of my research group back in the mid-1990s. If anybody can guess what the vehicle is, then I'm very happy for them to take a pot shot up at that in the chat function. But this is a carbon fiber vehicle body side that we developed in our lab in Nottingham. Anything coming up on the chat? Aston Martin Vanquish, yeah, absolutely. So thanks for that, Andrew. So this is the Aston Martin Vanquish. It is the so-called Bond car. I can't remember which movie it featured in, but we did a lot of the prototype development for the Vanquish in my lab. So the body sides and the crash box, front end and rear end structure. And it was a great privilege to be able to work on something that was as high profile as that, but also was as kind of real world as that. And many of the young research engineers that you see in that picture went on to join Aston Martin and other organizations who were developing those kinds of materials. Let's scroll forwards a couple of years. So it was, again, a great privilege to be able to go to China and to restart that whole activity. And this is the research group that we built up in China in 2016 and 2018 on a bit of adventure sporting, a combination of climbing and crag cleanup in the first shot, and then in one of China's, South China's best known ski resorts in the second picture, where you can enjoy some fine skiing for about 5 days of the year at a slope angle of about 2 degrees, but don't knock it if it's the nearest thing for a few thousand miles. So that was great fun. But I want to sort of dive back a couple of thousand years, because I want to look at the early development of new materials and to find the roots of our noble calling. I think you've got to go back to the alchemists. And of course, the alchemists were working not just in Europe, but also in Central Asia and East Asia, where they had these completely undeliverable but very universal aims, which were the transmutation of metals, so turning lead into gold, creating an elixir of immortality, creating a universal panacea to cure all diseases, and the development of the universal solvent. And of course, most of it was a complete waste of time. But was it? Because some really extraordinary discoveries came out of that in the pre-Christian times. Some really amazing chemistry done in what is now modern Iran. Of course, many incredible discoveries done in the early dynasties in China, and I'll mention some of those later. But more than anything else, I think that alchemy, rather than developing important new materials, it provided the basis for modern chemistry and modern pharmaceutical sciences. And if I've got time, I'll come back to those themes. So here is another question for you. What, in your opinion, which new material do you think has had the biggest impact on civilization, whether that be positive or negative? And let's just pause on that and have a look at the chat to see if we can get some interesting suggestions on what the most important new material was, how it influenced society, and where it came from. Because there's no uniquely right answer to that, of course. So we got plastics from a few people. I think that yeah, you know, putting my hand on my heart as somebody who's been involved in the development of new polymers, I take some responsibility for the fact that some of the influence of plastics has been and is pretty horrible, and we'll come back to that. Cement, titanium alloys, we've got reusable materials, Peru's tossed in the atom. So I think it's a very basic material. It's a material that probably we've all used today in one form or another. A material that in our youth we probably used a lot of, but as every day goes past, I hope we are using less of it. And for me, it is this stuff. Scientifically, it is cellulose fibers that are bound together by a clay and polymer matrix, and it's paper. And it exists in different forms. It can be made from different sources. It's been around for a couple of thousand years. But I think paper is probably, arguably, the first important synthetic material. Probably goes back a couple of thousand years in China, although it's almost certain there were parallel inventions in other societies. You know, we can think about ancient Egypt and their use of paper-like products. But paper was important for a couple of reasons. First of all, it was really important for China at that time. And why? Because at that time, people were writing, but they were writing on silk. And once the Chinese started writing on paper instead of silk, it meant that they could export their silk and produce huge export earnings. So the invention of paper was indirectly responsible for China's first great golden age. And it actually took quite a long time to spread universally, at least into Europe. But once it did, then paper enabled mass learning, literacy, the dissemination of news, the dissemination of scientific findings, and like the democratization of knowledge. And so for me, that's why paper was a real game changer. And of course, China was a great source of new technology, and particularly new materials technology. I already mentioned gunpowder or black powder, but I think the next most important development that came out of China was porcelain. And probably not many people know what porcelain actually is, but it's not a clay. It's a technical ceramic, and it's made by a fairly sophisticated blend of different minerals, which are then fired like a clay to make a technical ceramic. So unlike materials like terracotta and other mined clays, porcelain has got a controlled porosity. It's relatively tough. It's got a very high temperature resistance. And for that, it has been used in a lot of really fundamental new technologies, like in high current electrical insulation. And really crucially at this time, it was the material that was used as filters in the first virology studies that were done in the 19th century. And virology is a discipline which, of course, is enjoying very much the public attention at the moment because of the present pandemic. And we will come back to the role of new materials in controlling virus spreading a bit later in the talk. So if we want to look at, instead of ancient new materials, we want to look at modern new materials, then we've got a huge range of different materials that we could pick from. I just want to look at a few that I think are particularly significant in the way that they have changed our lives within a generation, really. And the first one has really got to do with energy. Now, as population continues to grow, especially in the tropical regions, and as populations continue to urbanize, especially within the tropical regions, then our energy demands are growing and growing and growing. And the number is probably pretty meaningless, but 650 million terajoules by 2035. And it's worth pausing and thinking about that there is absolutely no way that we can deliver that with any of the so-called conventional energy sources. Fossil fuels aren't going to go anywhere near it. Wind isn't going to go anywhere near it. Tidal isn't going to go anywhere near it. The only thing that can get close to delivering that in a sustainable way is solar energy. And of course, solar energy is great because it's, in inverted commas, free, but of course, solar energy, like all of the so-called renewables, is intermittent. We only get a decent level of output when we're in daylight hours, when the sun is shining, and when the sun is shining at a reasonable level of incidence on our solar panels. But all the ways of capturing solar, all the ways of storing solar, and all the ways of converting solar all rely on materials technology. And the first bit of technology we need is the capture technology. And solar panels, for the last 20 years or so have been a common sight in our countryside, on our buildings, even on our mobile devices these days. But actually, the photovoltaic effect was first published in 1859. So let's just think about that. That's like 150 years of technology incubation to get from initial discovery to deployment in the mass market. And for the important materials technologies we use these days, that's very often the case, that we're looking at 100 years to get from the lab into the factory and onto your car or vehicle or boat or whatever. And the other thing to say is, actually, you know what? The technology that you are using on the roof of your house is pretty rubbish. And why is it rubbish? Because it's only capturing about 20% of the incident solar energy that is radiated and incident on your panels. And why is that? It's simply a thermal effect, because when the sun shines on your panels, they warm up. And as they warm up, they become very, very inefficient because of the crystalline silicon that they're based on. And of course, it's very promising that there are new materials based on gallium arsenide and a mineral called perovskite that will probably, in our working lives, double the output of any solar panel, which is really exciting. But the next thing is, what about this supply and demand issue, and the fact that you've only got an energy output when the sun's shining, when the wind's blowing, or when the tide's running. And so, put it this way, if your household electricity was directly coupled up to one solar panel, however big it is, it means that you can only watch TV, use the internet, heat water, run your charging devices when the sun's shining. How useful is that? And the answer is not very useful at all. So as well as finding ways of efficiently capturing energy, we've got to be able to store it and then to release it quickly and on demand. And the way that we've done this classically at a macro level is by something called pumped storage, where we take a reservoir and we use massive pumps to pump the water in that reservoir up a hill. And then during times of peak demand, we let the water run back down the hill and use it to generate electricity through a water turbine. It's super basic and it's not very efficient. And of course, the other thing that we do is to store energy at a micro level with lead acid batteries, which is slow, polluting, very low power density, and not a great environmental solution. So imagine a phone battery, for example, that would charge in 1 second. We'd all go out and buy one, right? And so the answer to problems like that are devices that rely on new materials. They're sometimes called supercapacitors, they're sometimes called supercabatteries, and they use new materials like carbon nanotubes and graphene, which have got massively high surface area to charge and discharge in a matter of seconds instead of a matter of hours. So that's a really exciting development. And then the other exciting development I want to talk about is fuel cells. So we're very comfortable, if that's the right word, with the idea of burning hydrocarbons to generate heat and power. And here's a very simple hydrocarbon, the most simple. It's a methane gas reaction. We combine it with oxygen and it produces heat, but it also produces byproducts, carbon dioxide and water. So water's okay, but we all know the issues with carbon dioxide, a greenhouse gas, and something that a lot of scientists around the world are working very hard to mitigate the effects of in all sorts of ways. But let's not talk about a hydrocarbon reaction, let's talk about hydrogen. So if we took that same hydrocarbon gas and instead stripped out the carbon, and we instead burned the hydrogen, then what have we got as a byproduct? Something we can drink, right? Nothing but pure, clean water. And that's when people talk about the hydrogen economy and hydrogen fuel cells. That's what they're talking about. They're talking about a device that could give us a pretty high power density with no pollutants, but instead of giving us heat as the product, giving us electricity as the product, because we do the combination with oxygen in a very special way. We do it by ionizing the hydrogen and ionizing the oxygen and using the electrons that are freed from that ionization process to drive an electrical load. And that's the basis of a fuel cell, and it's dead simple. That you take a device that you pump hydrogen in one side, you pump oxygen in the other side, you've got an electrical output. So if you like, it's a battery that doesn't have the consumable metal anode and cathode, but all it's producing is electricity and water. It's a little bit more expensive than a conventional battery because we've got platinum and nickel as electrodes, but it's clean power, and it's clean power with a super high density compared to even a lithium ion battery. But the question is, how do we store our hydrogen? And if anybody is old enough to remember being told about rationing by their parents or grandparents, they might have seen imagery like this, where during World War II, buses and cars were driving around town with these great big gas bags. on their roofs, and they were using gas bags to replace the petrol tanks, and they were using town gas, which wasn't rationed, to drive their engines to replace petrol, which of course was subject to rationing. So can we do the same thing with hydrogen? Well, in principle we can, but spot the problem. Hydrogen gas just happens to be a little bit explosive. And over a very, very wide range of mixtures with air, it can be formed an explosive mixture triggered by a spark, triggered by heat, or even triggered by sunlight. And you probably have seen this iconic image from 1937, which was the famous airship, the Hindenburg. And if you were flying around the globe in 1937, then your aircraft of choice would have been an airship. And that airship would almost certainly have been carrying hundreds of thousands of cubic meters of hydrogen. And the crazy, crazy thing was that hundreds of these airships met a similar fate to the Hindenburg. It's even also rumored that the canvas that the Hindenburg was covered in was doped with a compound called cellulose nitrate, which, if anybody was reading the news recently, is similar to the material that was responsible for the Beirut explosion. Does anybody know where that, okay, so here's I'll give you, I think, a hint. Where was that classic image reused in a popular culture context? Let's have some memories in the chat, if possible. Anybody seen that before somewhere? Maybe somebody who was a child of the 1960s, like me. No, I don't think we're going to get it. So let's go back. Oh. Yep, and it was, of course, on the album cover. It was nicked for the album cover of the first Led Zeppelin album, which remains, I have to say, in my collection. Okay, so storing hydrogen is pretty tricky. You could store it as a liquid, but then that needs to be maintained at minus 240 Celsius and a couple of hundred atmospheres of pressure. So you're not going to want to have that in your car, and you're not going to be allowed to have that on your personal mobility device or carry it on the MRT or anything like that. So instead, material scientists are developing and have developed porous solids like carbon nanotubes and metal hydrides that will somehow absorb that hydrogen and store it at super high densities safely and at room temperature and at ambient pressure. So another important contribution from material scientists in terms of delivering new energy materials. So now let's talk about burning energy. And I mentioned the huge contribution that electrical lighting has made to our society, and it has enabled universal education at home, road safety, personal safety in urban settings, and most of it now is LED. So in which year did you buy your first LED light bulb? And does anybody know, without resorting to Google, when the LED was first invented? So we're not getting any LED memories yet. So I reckon that I bought my first LED in about 2012, and I reckon it probably cost me about 5 GBP. Here's the thing, is that the first LED was actually developed in 1927. What about that? So that's a material that's taken about 100 years to get from lab into serious commercial production. And why is that? And it's a very simple reason, and that is that for about the first 70 years of their lives, LEDs were only available in red. And it's only a certain category of user that wants a red LED. And it was only in the 70s and 80s when material scientists started developing ceramic coatings for the semiconductors that enabled them not to emit only red spectrum, but first blue and then white light, that it realized its commercial potential. And of course now, massive commercial market, massive impact on energy savings and all of our lives. So I'm just conscious of time, and I'm going to go, I think, probably, Karen, for about another 10 minutes.
Okay, Chris.
And if we talk about electrical lighting, it leads me back to where one of the things I came in, and that is back to my old friend carbon fiber. And carbon fiber was important enabler of electrical lighting, because Swan and his English co-inventor, Edison, his English co-inventor Swan, both used graphite fibers in their proto light bulbs. And that helps us to bridge into the use of carbon fibers in structural materials. And I'm really grateful to Abhishek for mentioning this during the staff sharing earlier on, because he introduced the idea of carbon fiber composites as structural materials when he showed us those black bits of F1 cars that he had picked up after F1 crashes. And this is a material that's only been around since 1960. And it's a material which relies on the alignment of graphite along the chain of a very small fiber that we looked at in the earlier picture. And one of the amazing features of carbon fiber is not just its specific strength and its specific stiffness, but the fact that it can absorb a heck of a lot of energy. And the reason why most of the F1 crashes that Abhishek showed us earlier on involve their drivers getting up and walking away from the crash is because they've got carbon fiber crash energy absorbing structures. And the reason that carbon fiber composites are so good at absorbing energy in an impact is because when they get crashed, you absolutely destroy every last atom of that material. If you put a Coke can or an aluminium can in place of that carbon fiber cylinder that's being shown there, when you crush it, and you can hear me crushing a can here, then it buckles. And buckling is a really inefficient way of absorbing energy. But crushing is really, really energy efficient. And that's why carbon fiber composites are so much better than any metals you would ever find for an F1 car. And you'll see the same thing, carbon fiber composites now ubiquitous in consumer goods like fishing rods and skis and high-end road bikes and so on. And I'm sticking with advanced structural materials and accelerating towards the end here now. And let's talk about aerospace again, because remember those happy days when we used to fly, and we would fly on an aircraft that was powered by a jet engine. And a jet engine, whether it's a turbofan or whatever type of gas turbine, relies on gas turbine technology. And gas turbines burn a lot of fuel. And if you look at the global airline industries, then 24% of the airline costs in a normal year involves kerosene. So we've got a global fuel bill of $188 billion. And so if we can make a small gain in gas turbine efficiency, then we will save the global aerospace industry's cash, and we will save ourselves as consumers cash. And that depends on engine design. And engine design depends on one critical factor, and that is the operating temperature of the gas turbine. So when you look at the engine on any aircraft that you get on, what you normally just see is the fan, those big black blades at the front of the engine here. But the really important bit is the hot end, as the engineers call it. It's the gas turbine. And the gas turbine involves a wheel with a bunch of these things on it, and these are gas turbine blades. And the hotter that we can run the gas turbine, the more efficient the thermal efficiency will be. And here is the scary, scary thing. When you take your next flight on any commercial airliner, the gases that go into the turbine will go in at about 1350 Celsius. The nickel alloys that the turbine is made of have got a melting point which is about 35 degrees lower than the gas temperature. So think how terrifying that is. That not only are your turbine blades within a few degrees of melting, but actually the gas inlet temperature is hotter than the temperature that you could put those blades into a furnace and cause them to melt. And the reason that is made possible is because of ceramic coatings and advanced cooling technologies that material scientists and engineers have developed to enable the turbine to run at a higher temperature than the melting point of the alloy blades. And to take that a stage further, the other quite incredible thing that materials engineers have done is they've managed to cast those blades into a single crystal rather than lots of tiny, tiny crystals, which means that the time-dependent deformation of those blades under load has been more or less eliminated, which makes them much safer, much cheaper to maintain, and really a masterpiece of materials engineering. And then getting towards the finishing line, very topical. Another very topical issue is the idea of antimicrobial surfaces. You know, we're all going around trying to open doors with our elbows at the moment. What about if we had an antimicrobial surface, an antiviral surface that would naturally kill or shed bacteria or viruses from those surfaces, using the idea of the lily leaf, the water lily, which has got this kind of high purity due to a natural surface engineering. Already we've got devices that use that same technology being used in hospitals, on medical devices and so on, and probably quite soon on an MRT station or car near you. We've also got engineering materials being used for tissue engineering to grow new organs, to assist people who've got congenital defects and provide them with kind of organ-farmed implants that will help them to either have a higher quality of life or extend their lives. We've got resorbable medical devices that use materials technology to resorb inside the body. And then I think I'm just going to finish with this last one. Another little quiz question. What is the strongest material currently known to science? And one of the things it's not is a clue in the picture. It's not spider silk, which is an answer that often gets thrown out. Any suggestions for what the strongest material known to science might be. Nanotubes. Nanotubes, carbon nanotubes would have been right about probably 15 years ago, when Liang is saying graphite, which is kind of almost right. And the answer is, oh no, Karen, not titanium, no. It is, of course, a single atomic layer of graphite. And what do we call that? We call it graphene. And graphene is interesting from lots of different perspectives. It's got the highest melt temperature of any known material. It's got the highest tensile strength of any known material. It's got the highest thermal conductivity of any known material. It's got the highest electrical conductivity of any known material. It's been known for quite a long time, but it became really big news when Geim and Novoselov won the Nobel Prize in, I think it was like 2005 or something. And so now graphene is a commercial proposition. It's being used in electrical devices. It's being used for like rewritable paper and stuff like that. Interestingly, our friend Novoselov is now a Singaporean. We all know that Singapore doesn't actually make anything if you can buy it. So I think about 3 years ago, it bought Novoselov from Manchester, where he now runs his lab in NUS. Just wanted to share a little bit of fun about his partner in crime. Fun facts about Andre Geim. Andre Geim, 5 years before he won the Nobel Prize, actually won the Ig Nobel Prize. And he is, I think, the only living scientist to hold both a Nobel Prize and an Ig Nobel Prize. And he won his Ig Nobel Prize for carrying out magnetic levitation experiments with a live frog in a 16 Tesla magnetic field. If you go on his personal website, you'll also see there are other interesting things about Andre Geim, in that in 2001, before the Nobel Committee honored him, he also named his pet hamster as a co-author on a research publication, which again was about levitation techniques, and you can see the citation there. So fun facts about famous Russian scientists. Okay, let's wind up. What can we learn from all of this? I think the key lesson is that of course we rely on materials as everyday citizens, but those materials will only have an impact on society if we can make useful devices at an affordable price. And many of the things that we rely on as technology solutions today were around like 150 years ago. And many of them were discovered by accident. They suffered the same problem with the valley of death that any other technology innovation suffers from. What made the difference for the materials that did succeed? I think I've mentioned a few things. One is better instruments, better ability to do high throughput screening, more digital control, better connectivity between researchers, so communications technology, fast moving electronics industry that was kind of driving a lot of this development, not just in university labs, but in industry as well. And of course, an increasing need to manage finite resources. Who does all this stuff? It's not just material scientists, it's also chemists, mechanical engineers, physicists, pharmacists, food science, people. It's basically people like you. And maybe, you know, if you've got a few minutes, Karen, for discussion, if you could invent a new material tomorrow, what would it do? A few things that occurred to me. Well, pretty high up the list has got to be antiviral protection, carbon capture and storage, producing fuels from crop waste or municipal solid waste, of course, accelerating the production of new human organs, digesting marine plastics. I know that you would vote for that one, Dean. And if we had time for part 2, I would show you some interesting solutions to that. Receding marine coral, we've also talked about with our JCU colleagues. Producing affordable proteins with a low carbon footprint. Or maybe just replacing you in your next Zoom meeting. So those are my bits of food for thought. I did have a part 2, but I'm going to park it there and say thanks for listening. Thanks to all of those generations and generations of researchers and collaborators that helped to produce a few of the results that I shared with you, and for many of my academic colleagues in Singapore, in Australia, in China, in UK, who have helped to keep me sane with friendship, with ideas, with sharing, and with your support. So over to you, Karen. Thank you.
Thank you, Chris. That was wonderful. I'm not really sure that I'm really happy that I know about the melting points of nickel alloy in planes, but we'll chalk that one up. And I think, you know, given the interest, I think we probably need to rebook you for part 2, because I know certainly all the marine people would turn up if it was about eliminating plastics from the ocean. So look, there are a couple of really good questions that came up. If you don't mind, we'll just spend a little bit of time on them. So the first one was from Denise. Is it possible to replicate a material at the fibre level through 3D printing?
Yeah, so if my audio is still good, that's a really interesting question, and quite a lot of people are working now on 3D printing, not of polymers, but of fiber reinforced polymers. And what I would say is yes, to some extent, but it's kind of not a universal panacea. I think what is more interesting is if you think about 3D printing and you scale it up like 1,000 times, so that you've now got a 3D printer which is the size of a double-decker bus. And so that 3D printer is now effectively building an aircraft fuselage. And that's happening now. That's happening in the industry. And you wouldn't call it 3D printing, you would call it 3D tape laying. But like, you know, the A380 fuselage is built like that. It's not called 3D printing, but it basically is 3D printing. And of course, the other really exciting direction with 3D printing is printing with biological tissue and starting to build replacement organs with something that looks not too different from the conventional 3D printing, but laying down bone cells or liver cells or even skin cells.
Wonderful. We've got a couple of questions from Edwin. The first one is, which material has similar properties to carbon fibre but is much cheaper? Is there an alternative material suggestion?
Yeah, it is an interesting one. So the reason that the people use carbon is because they want stiffness, usually, not so much because they want strength. And there are also some competitors. So what I would call aramid fiber, what you would probably call Kevlar, is similarly stiff to carbon. It's not really any cheaper. And there is another material which is almost as stiff as carbon, and actually quite a bit lighter, is high density polyethylene, which sounds mad, right? Because when I say polyethylene, you think plastic bags. But if you take your plastic bag material and you heat and stretch it in a certain way, then you will orient the molecules and produce a material which is super, super stiff. But of course, the problem is that instead of having a melting point of about 900 Celsius, like carbon fiber, it's got a melting point of about 50 degrees. And so it's never going to find its way into, even a moderately high temperature application. But it is used extensively in stuff like the marine industry. It's used for ropes, for example, on windsurfers and things like that. You might know it as Dyneema, but it's basically high-density polyethylene.
Okay. One from Abhishek. So Abhishek's asking, the lead-in time from lab to market seems to be too long. That seems to be one of the issues raised, which equates to similar to COVID-19 vaccine today. What are your thoughts on shortening that lead time?
It's interesting, isn't it? So, a lot of the materials that I cited in that little talk, like things like PTFE and the LEDs, they're, I suppose, an accident rather than something that's been, done as a kind of a focused set of experiments looking to find a particular solution. They're really answers looking for a problem to solve, and that's why they sit around for so long. But when you get to critical needs, like I think like wartime is a very good example. And you look at the records of countries like Israel, which have lived under this heightened sense of security for a couple of generations. Their productivity in terms of getting of patent generation, IP exploitation is way, way higher than that of countries that might be equivalently wealthy, but they've had periods of relatively stable democracy. And there is something about chaos and disruption driving invention, driving creativity, and driving a greater focus to exploitation.
Okay. There's a couple of questions. They come up as anonymous, but I think they're good questions, Chris. So the first one is, what are the advantages of carbon nanofibers over carbon fibers?
The thing that we didn't really have time to get into is why is scale important in the properties of a material, and why is so graphite, carbon nanotubes, carbon fibers, they're all the same thing. And then even like a block of charcoal on your barbecue grill, they're all the same thing. They're all graphite. But one of them has got like the most amazing properties of any material, and the other one, like the stuff on your barbecue grill, is just junk. It just crumbles in your hand. And it's all about defects. And the fact is that as you go down in scale, then first of all, materials get purer. And secondly, they become freer and freer from defects. And even though carbon fibers have got amazing strength, amazing temperature capability, amazing stiffness, they're full of flaws. And the reason why Rolls-Royce went bankrupt in the early 70s was because they were using early generation carbon fibers that were full of flaws. And it was really only when, as an industry, we learned how to control the incidence of flaws, even at the microscopic level in carbon fibers, that they actually became reliable and commercially important. And so, and actually the same goes for glass. So glass fibers are very useful engineering materials. They're very strong, they're very tough. But actually glass as an engineering material in plate form or in brick form is useless because it's full of flaws, and therefore it's very brittle. And it's only when we can control defects, that we get useful, reliable, and strong materials.
Okay, well, see what you can do with this one. So this is another anonymous attendee. Are we close to developing pop culture inspired materials such as Iron Man's nanotech equipment or Captain America's vibranium that absorbs kinetic energy?
Yeah, it's a really interesting question. So part two, if we ever do that, Karen, is about Robert Boyle's desiderata, which, what the hell does that mean? Everybody thinks it's about his 24 wishes. And Boyle was an Irish physicist back in like 1650 who wrote down the kind of 24 things that he'd dream of discovering, like, you know, things like the cloak of invisibility, like, you know, the transmutation of metals, and the kind of sort of improbable material that you talked about. And actually, it was all fantastic stuff to Boyle in those days. And none of those wishes were realized in his lifetime. But the thing is that he didn't know what he didn't know. So whilst he put down things like, you know, the ability to fly or to function underwater, or to cure wounds at a distance, or to do transplant surgery, because those were things that he could see could one day be possible. He couldn't see the things that he didn't know might be possible. So he didn't say, you know, I'd like to invent this portable device that you can put to your ear and talk to your friend on the other side of the world, because it was just so far beyond his ken. And there's got to be plenty of stuff out there that, even though we live in this super technologically driven age, that is still just beyond our ken. Because, you know, you start putting mobile technology together with plastic, electronics, put together with, like, you know, the strongest material that we can ever produce, and then putting that together with advanced bioengineering and stuff, then of course there's stuff that we just haven't, you know, built a consciousness around yet.
Look, Chris, there's 5 more questions. You've still got an audience of sort of over 50. So are you happy to, if we just sort of cut it off after these 5, are you happy to?
Yeah. If you want to kind of close the book, as it were, and we'll see if we can have a go at knocking those off.
Okay. So this one's just come in. Can you briefly explain how carbon nanotube can be manufactured using local materials?
Yeah. So carbon nanotubes. So if you want to make a carbon fiber, you take a polymer fiber, and then you oxidize it. So basically, you heat it in the absence of oxygen. You do a few other things as well, and you turn something like an acrylic fiber into a graphite fiber. If you want to do the same thing to produce a material which is only a few atoms thick, in the form of a nanotube or a buckyball or one of these other nanostructures, then you've got to do it by chemical synthesis. You've got to do it by mixing chemicals together in such a way that you get a reaction which forms the nanotubes as what we call a precipitant, which means a solid product of the chemical reaction. So we do it by a synthetic method rather than a thermal method.
Okay. One from Edwin. Theo, what notable and particular qualities should new materials aim to achieve?
Oh my God.
Yeah, in the shortest possible time, because
I mean, there is no single answer to that. You know, if you're a materials engineer working in the biomedical industries, then you are looking for, compatibility with, with human tissue. You are looking for low levels of toxicity and inflammation. If you're an aerospace engineer, you are looking for high temperature capability, high strength, low density. If you are working in the consumer industries, you are looking for, crudely, something that's got sex appeal, something that can be manufactured at volume, at an economic scale, and something where, as a manufacturer, you can keep the IP moving ahead of the competition. So, yeah, there's no single answer to that, too.
Okay. So Andrew asked, with some countries banning ICE cars, such as the UK in 2035, and the current constraints on electric vehicles in terms of charging time, do you think the future of the car could be the use of the supercapacitor or hydrogen fuel cells?
Interesting question. My sense is that it depends what kind of vehicle you're talking about. If you're just talking about the family car, then I think that, excuse me, a predominant reliance on the kind of classical Mark 1 EV with lithium-ion batteries is probably going to be the main kind of weapon of choice for the time being. I think that you will see more use of fuel cells, but I think that you will see it in a selective way. I think that you might see it in specialist service vehicles. For example, something like a fire engine that needs to, go to max power in a very short space of time, and can also justify the high intrinsic costs of things like fuel cells. I think that you might also see fuel cells being used in things like public service vehicles, like MRT is a classic example, where for a fact that vehicle is going to spend half its life accelerating and half its life braking. And therefore, if you don't do something to capture the energy that's otherwise thrown away during the braking cycle, then you need something like a supercapacitor. So they make economic sense. You can justify the high capital cost. And also you've got to think about the security issue, because if you're starting to put devices that have got large amounts of platinum and nickel in them, then at least on the streets where I grew up, some Jack the Lad is going to find a way of making money out of that. I do remember in the early days of catalytic converters, coming back from holiday for 2 weeks, getting in my car, firing up the engine, thinking, shit, that sounds a bit loud, and looking underneath to find out that somebody had come along with a cutting torch and removed the catalytic converter in my exhaust system. So these things have also got to work in a human context.
Absolutely. Last two. So Thomas has asked, it is said that the old-time favourite cast iron is a far better cookware than Teflon or ceramic, simply because it does not contain harmful chemicals. What are your views, please?
I think that's a fair comment, Thomas, and it is often the case that I mean, you wouldn't call cast iron a natural material, but that some of the traditional materials are actually pretty damn good. I wouldn't have picked the example of cast iron, but and you might have a view on this, Karen. What about the idea of the wooden chopping board? So probably most households now have got this lovely kind of block of low density polyethylene that they picked up at IKEA, that they chop their vegetables on. And it has been demonstrated that if you use, I think it was Beach in the published study, if you use a natural wooden chopping board, then the natural acidity of the lignin in the wood is a much better antimicrobial than any plastic that you can buy. So yeah.
Absolutely, I'd agree with that, but it does also too depend on how often people clean said wooden chopping board and maintain it, and what's vegetables fine, meat maybe not so much. Okay, lucky last question, and there are a couple of people that wanted to know the answer to this, Chris, so you're off the hook. Did Pierce Bronson ever have any comments about the Aston Martin Vanquish?
No, we got some fantastic publicity out of doing the Vanquish project, but it stopped a long time before it went anywhere near Hollywood. I mean, just the brand association with AML, which, I know the reality of it at the time. It was a pretty rubbish business in reality, but the brand value was very considerable. So we certainly dined out on that for a while. Did we make any money out of it? No, of course not. And did we get close to any Bond girls? I'm afraid not.
I expected to see you, and I was going to go back and watch it and see if you were an extra or something. But look, we will call it quits there, and I think, certainly due to popular demand, we might have to get you back to do part 2 of your professorial lecture, because we had attendees well up over the 60, and I think that the questions generated were certainly really good questions. So I look, on behalf of certainly the research team and everybody that's been a part of this, I'd like to thank all of the attendees for coming, and certainly Professor Chris Rudd for your time and your expertise and your generosity. As I said earlier, there's a quick satisfaction survey. If you wouldn't mind filling that in, we'd be truly grateful. And we look forward to seeing you for the 4th in our series, and we'll keep you posted when we will bring Chris back. Thank you for your time.
Thanks, Karen. Thanks, everybody.